We're going to talk about extrema on an interval, and also increasing and decreasing functions. Now, extrema, when we say the word extrema, what we're really talking about are the places where we have a maximum or a minimum of some type. And there are two types of extrema. We have absolute, sometimes called global extrema, or we have relative, and sometimes these are called local extrema. So let's just talk about what's the difference between these. Now, it's easiest to look at a graph or something and see the differences here. I've just given you a graph, and I've identified a few special points here on this graph. This point right here is the lowest point of all the points on the entire graph. This is the lowest absolute point of all those points. And so we would call this an absolute minimum. This is an absolute or a global minimum. All right. And we have, let's see, looks like this point right here is the absolute highest point of all the other ones. And so this would be an absolute maximum or a global maximum. All right, so we have some other points over here. It looks like, well, this one's not really anything. It's not the highest, it's not the lowest, it's not really anything interesting going on there except for the fact that that's just where the graph ends. If we look at this point right here, well, it's not the lowest point on the whole graph, but if we were to just sort of zoom in right here around that point, we can see it's the lowest point among all those around it. You know, over here, it's not quite as low as that one. Over here, it's not quite as low as that one. This would be the lowest point among all those that are immediately around it. So if we look at this locally, or relative to just that point right there, then that would be a minimum of some type. And that's what we call a relative minimum. And we can see that this right here, now remember, this was also the absolute max, but we can see that, you know, it also has this some kind of characteristic, whereas if I were just to zoom in right around this one right here, this would be the maximum among all the points around it. So this right here is not only an absolute max, it's also a relative max. So we can see the differences between relative max and min, absolute max and min, or if we want to use the words local max and min for the same thing as a relative, or global, then that's perfectly fine. Now notice I'm saying, hey, these points are the max or the min. Let me get a little bit more specific about that. When I say that this point right here is the absolute max, what I really mean is that the absolute max of the function is this y coordinate right here, right? When I say how high is it, I'm talking y coordinates. So the absolute max of the function is 0.4, and it occurs at x equals -1. Okay, so we are talking about the point, but really the max of the function is 0.4, and it is occurring at x equals -1. So a couple of observations here. One is that relative extrema always do this. They either go up and come down, or they come down and go up. You can think about it sort of like a roller coaster or something, right? This is where you're going up, and then you get that oh no moment up here at the top, and then it starts to go down. That moment up there at the very top, that would be your relative max. And then, you know, same thing here with the valley, where it goes way down, goes down, you hit the bottom, then you start going up again. That's a relative min. So relative extrema always do this type of thing. And, you know, this is a graph where these are all nice and smooth, but it could be that we have some kind of a graph that's not only doesn't have these nice smooth curves, but, you know, does this type of thing. You know, and so here we would have a max, and here we would have a min. Those would be relative maxes and mins. Looks like that would also be an absolute max. In this case, if this graph goes on forever the way it is right here, actually, you know, if the graph goes on forever in both directions, that wouldn't be an absolute max, because this thing would just kind of keep on going. You could never find the highest point. So, you know, if you have graphs that go on forever, often you can't find maxes or mins. Sometimes you can, sometimes you can't. On a closed interval, absolute extrema, those absolute maxes and mins, they either occur at endpoints or they occur at the relative extrema. So if I have a closed interval, in other words, you know, where I've got a closed dot over here, and I got a closed dot over here, and I'm just interested in what's happening in between those, then I can say that the absolute maxes and mins occur at the endpoints or at the relative extremas. And that's different from this kind of situation here, where if we have a graph that goes on forever, if I have a graph that goes on forever in one way or another, and it keeps going this way, I would never be able to find an absolute minimum in this case, because this graph just goes on forever, down this way. I could find an absolute maximum. There is a highest point, but there's not a lowest point on this kind of graph. So we're going to start off just by talking about closed intervals and see if we can just sort of figure out how to find those kind of maxes and mins first. Now, relative maxes and mins occur at special x values that are called critical numbers. And so a critical number, I'm going to call it C, it's a critical number if it is in the domain of the function and either f prime of c is equal to 0 or f prime of c is undefined. Now I want to point out there's two conditions here. There's two things we're watching out for. One is that it's got to be in the domain of the original function. C has to be a number that you could throw into the original function. And it doesn't cause any kind of problems. Zeros in denominators or negatives under square roots or anything like that. So it's got to be in the domain, and it's either where the derivative is undefined or where the derivative is equal to 0. So let's go in here and we're going to find all the critical numbers. We've got an example, f of x equals x to the fourth minus 4x cubed. We want to find all the critical numbers here. I'll first note that this is a nice little polynomial function. There's not going to be any places where f is undefined. There's not going to be any places here where where we can find things that aren't in the domain. In other words, the domain would be negative infinity to positive infinity. So we know that this kind of first condition here is already satisfied. Now we're looking for places where either the derivative is undefined or where the derivative is equal to 0. Well, again, this is a nice little polynomial function. If I find the derivative of it, looks like I get 4x cubed minus 12x squared, and there's not going to be any places where that derivative is undefined. So what I'm really looking for in this case is I'm looking for the places where the derivative is equal to 0. So I got f prime of x is equal to 4x cubed minus 12x squared, and I'm going to set that equal to 0. Well, we know how to do this. It's not too complicated here. If I factor out a 4x squared, looks like I would be left with x minus 3 in here. That equals 0. And so it looks like I'm going to set each one of these factors equal to 0. If I set 4 equal to 0, I don't get anything from that. If I set x squared equal to 0, I should be able to get a solution from there. And if I set x minus 3 equal to 0, I should be able to get a solution there. Okay, and so I get, looks like here, if x squared equals 0, I get x equals 0. And over here, it looks like I'm going to get x equals 3. Now, I want to point out one thing here. If you have x squared equal to 0, remember this is really x times x is equal to 0. And that means that you really have 0, twice here. You get x equal to 0, and you get another x equal to 0. The way we say that is we say that we have a solution here with multiplicity two. All right, so we have x equals 0 with multiplicity 2. And that's just because we have x times x is equal to 0, and setting each factor equal to 0, you would end up with x equals 0 twice. And so we don't write x equals 0 twice. We just say, okay, x equals 0, but the multiplicity of that is 2. And that's going to be something kind of important for us here in a little bit. So let's just kind of note that. Over here, I really don't have to write it down, but I would get with multiplicity 1, because there's only 1 3 that pops out of this solution here. So I've got my solutions. I found my critical numbers, and since I could plug those numbers into the original function, doesn't cause any problems there. I know that those are actual critical numbers. I don't have to worry about domain issues or anything. And that's been pretty straightforward. So let's look at another example. we want to find all the critical numbers of y equals 3 times x to the 2/3. Y equals 3 times x to the 2/3. Okay, well, I start off by thinking about the domain, because remember, all critical numbers have to be in the domain of the original function. And I know this is really the same thing as the cube root of x squared, and I can plug pretty much anything into that. Doesn't look like I'm going to get any domain issues here. Let's find the derivative. Let's see, y prime is equal to, okay, the 2/3 comes out in front. I've got a 3 that's already out there. I'm going to subtract the exponent by 1, so I get a negative 1/3. Looks like these 3's cancel out, and it looks like I'll be left with 2 over x to the 1/3. Okay, so I've got my derivative. And remember that the critical number, any critical numbers, are going to be places where the derivative is equal to 0 or where the derivative is undefined. So I look at this, I've got a fraction. Remember, a fraction only equals 0 whenever the top equals 0. So it doesn't look like I'm getting any numbers here where the derivative is 0. But what would make this thing undefined? Well, if I put a 0 down here in the denominator. So it looks like x equals 0 would cause the derivative to be undefined. I'm going to write that down. X equals 0 makes y prime undefined. And remember what we're looking for. Remember that critical numbers, these are numbers that are in the domain of the original function, and it's either where the derivative equals 0 or where the derivative is undefined. So we just found a number here that makes the derivative undefined for this problem. Okay, so x equals 0 makes this undefined. The question is 0 a critical number? Well, only if 0 can be thrown into the original function up here. And it looks like it can. If I stick 0 into here, I get y equals 3 times 0 to the 2/3. Remember, that's the cube root of 0, which is 0, squared, which is still 0, multiplied by 3, which is still 0. And so it looks like our critical number here is going to be, well, let me write down x equals 0. Okay. So let's put this all together. To find all absolute value, absolute extrema on a closed interval, we first find all critical numbers, and then compare the y values at all the critical numbers and at the endpoints. All right, so we're looking for, we've got some kind of a function out here, and we're wanting to find all the extrema. Now we've got to be doing this on a closed interval. Okay, and so what we're going to do is we're going to see if we can find all the relative extrema, all the critical numbers, which will identify where these things are happening. Okay, so I've got a number here, and I've got a number here, and I'm just going to call this, I'll call this x1, x2, x3, whatever number that is, we'll call that x4. That means that I've sort of narrowed it down to 4 numbers. So to find all the absolute extrema on a closed interval, we're going to find all the critical numbers, and then compare the y values at those critical numbers and the y values at those endpoints. So we're just going to look at each one of these 4 points and say, well, which one's the highest? Which one's the lowest? That will give us our absolute extrema. Okay, so let's do it. Let's go in here and find all the absolute extrema of f of x equals 2x cubed plus 3x squared minus 12x plus 1. And we want to do that on the interval from -4 to 2. So, well, we're going to go in here. First of all, we're only interested in what's going on between -4 and 2. So we see we've got our endpoints here. Okay. And we're going to need to find our critical numbers. So we know that comes from the derivative, f prime of x. Looks like we get 6x squared plus 6x minus 12. There's my derivative. I'm going to set that equal to 0. And remember, critical numbers are the places where the derivative is undefined or where the derivative equals 0. Well, I'm not going to get anything here that's undefined. I can throw any number I want to into here. And so I'm not getting anything from that part of it. But I can find where this thing equals 0. I'm going to start off by just factoring out a 6, just to simplify things a little bit. Do a little bit of factoring. So it looks like I get x plus 2 and x minus 1. And it looks like from there I get my solutions, right? If I set everything here, each one of these factors equal to 0, I don't get anything when I take 6 and set it equal to 0. That doesn't make sense. So nothing comes from there. X plus 2 equals 0 gives me x equals negative 2. X minus 1 equals 0 gives me x equals 1. I'll just sort of make a mental note here that remember each one of these solutions are appearing with multiplicity 1. They just appear once. Okay, and I promise that's going to become relevant here in a minute. But okay, fine, we got that. Looks like we got our critical numbers. So I'm going to go in here and make myself a table. And I'm going to just take note of what numbers are important to go in here. What are the x values that are important here? Well, remember that to find all the absolute extrema on a closed interval, we're first going to find the critical numbers and compare all the y values at the critical numbers and at the endpoints. So the numbers we're interested in are negative 2, positive 1, negative 4, positive 2, and so those are my x values over here. Negative 2, positive 1, those are the critical numbers. Negative 4, positive 2, those came from the endpoints. And all I've got to do now is just go in here and look at the y value. Remember, the y value comes from the original function. And I'll just compare that, see which one's the highest, which one's the lowest, and that'll give me my absolute extrema. Okay, so I'm going to do this just by going into my calculator and just plugging these things in. Now I've gone into my y equals, I've already put this function in here. And so I'm just going to look at the table and plug these values in as my x values and just see what those y values are. All right, so I'm going to go to the table command. So that second graph takes me here. Oh, it looks like I need to do a little setting up here. This is automatically just sort of putting in some different x values and give me those y values. I could pick out a couple of these things here, like alpha of 1 looks like that's going to be negative 6. But really I want to be able to plug my own x values in. I'm going to go to the table setup. So second window takes me here. And if I set the independent variable to ask, then in the table it's going to ask me what values do I want. So let's go back to the table. Second graph takes me to the table. And so what values do I want? Well, I want negative 2. I want 1. I want negative 4. And I want 2. And so basically I've got exactly what I want over here. I want these y values. So I got 21 for negative 2. I've got negative 6. I've got negative 31. And I've got 5. Okay. And so from here I should be able to identify my absolute extrema. Looks like the lowest y value occurs right here. So this is an absolute min. And the highest y value occurs right here. And so I've got an absolute max that comes from here. And that's it. I've identified my absolute extrema, my absolute max and mins on this graph. And if I go over here and just take a look at what that graph looks like, I can see this happening here, right? Here's the point. Let's see, negative 4, negative 31. 1, 2, 3, 4 is way down here. All right. And it looks like the absolute max is occurring here at negative 2, 21. So that's occurring right here. And I could identify these other points as well, but I can see, hey, this is the lowest one. This is the highest one. I've done what I've been asked to do. Okay, so let's talk about increasing and decreasing. F of x is decreasing if the derivative is less than 0, and f of x is increasing if the derivative is greater than 0. So let's just kind of think about the sign charts here. Let's think about some implications from this. All right, suppose that I go in here and this is just going to be an x-axis here, and I've found some critical number somewhere. Let's just call it c. All right, so this is a critical number. And suppose that over here the derivative is negative. And it hits that critical number, and now over here the derivative is positive. Now think about what that means for the graph. That means that for the graph that it's coming down, it's decreasing until it hits that critical number, and then starts increasing. Well, from that information, if it's decreasing, hits a critical number, starts increasing, I can see that what that really means here is that I've got a relative minimal. And I can identify that. I don't even have to look at the graph or anything. I can identify that just from the fact that I know it's decreasing and then it starts increasing. Well, okay, let's consider what happens if I've got my critical number here, and what if it was increasing all the way over until I hit that critical number, and then it starts decreasing? Well, we could draw some information from that as well. The information we can draw there is that it's going up, hits a critical number, starts going down. Looks like I've got a relative max in this case. Now, there are some other possibilities. Other possibilities are that maybe we've got something like this. Maybe it's decreasing, hits a critical number, and then it's decreasing again. Or another possibility is maybe it's increasing, hits a critical number, and then it starts increasing again. And you can kind of imagine what that kind of graph would look like. Let's think about this one. All right, so I've got a graph that's decreasing, hits a critical number, which means that the derivative is probably 0, so it kind of levels out, but then it starts decreasing again. Or it could do the other thing over here, right? It goes up, levels out, and then starts increasing again. So, we've got these kind of possibilities here, and you can see that we don't get relative maxes or mins occurring for these. For these up here, if it's decreasing and then it starts increasing, then great, I've got a relative min. Or the other way around, I've got a relative max. But sometimes, and just by looking at these sign charts, I can see that I don't really get either one. And so what we've got here is we've got the first derivative test. And the first derivative test tells us which critical numbers correspond to relative minimums, which correspond to relative maximums, and which correspond to neither one. And we do that just by looking at these sign charts up here. Okay, so I want to go back and reconsider. We saw this this type of we have these types of equations right here that sometimes we have to solve. We saw one earlier where we had the x squared, and that kind of led to two different zeros. Let's just think about these for a second. If we're going to solve this type of equation, the solutions in this case, well, we would set everything equal to 0 here, so we would get 5 equal to 0, which doesn't lead to anything. 2x minus 1 squared equal to 0, so we'd get 2x minus 1 squared, which equals 0. And we would also get x plus 4 cubed, which equals 0. Now, I think you can probably look at this and say, all right, well, I can get my solutions from there. 2x minus 1, if that equals 0, I get x equals 1/2. And over here, I will get negative 4. So that's not too tough to do. Let's remember that there's really two 2x minus 1s showing up here. 2x minus 1 times another 2x minus 1. So when we set 2x minus 1 equal to 0, yes, we get x equals 1/2, but it's actually showing up twice. And we call that multiplicity. Let's see. Okay. Multiplicity 2. And over here, I think you can see that we would get a solution, x equals negative 4. But in this case, we would get multiplicity 3, because we really have this as x plus 4 times x plus 4 times x plus 4, and each one of those would give me a solution of negative 4. So here's a cool fact. In the sign charts, now remember we're talking about these sign charts here from the derivatives, the signs in a sign chart only change when the multiplicity is odd. The signs do not change if the multiplicity is even. So in other words, when we go back and look at these sign charts right here, if we have a case where, negatives turn to positives, the sign changes, that means that at that critical number right there, the multiplicity of it was odd. And the same thing here, the multiplicity here was odd because these signs are changing. However, in these cases here, where we don't get relative maxes or mins, the multiplicity was even for this critical number. And the same thing here, the multiplicity was even. So that's a nice little trick to know, a little thing to know, because when we're constructing these kind of sign charts, it's nice to know whether the sign is going to change or not. It just kind of saves time, and we'll be able to see whether we have relative maxes or mins, or we doesn't correspond to either one of those, just by looking at the multiplicity. Okay, so let's look at an example here. I want to find where f of x equals x to the fourth minus 2x cubed is increasing and decreasing, and I want to identify all the relative extrema. Well, I know that I'm going to be looking at my derivative here. So f prime of x is equal to 4x cubed minus 6x squared. And I'm going to, let's just go ahead and factor that. Let's see, I could factor out a 2x squared from that, which would leave me with 2x minus 3. And there's my derivative, and I'm going to set that equal to 0. And so it looks like I would get a couple of solutions here. It looks like if I set this equal to 0, I'm going to get x equals 0, and that's going to happen with multiplicity 2. And here I would get, let's see, the 3 would go over, that would give me x equals 3 halves. And that would happen with multiplicity 1. Okay. And we usually don't write down the multiplicity 1s, but that's okay. I'm doing it in this case. All right, so what I'm going to do now is I'm going to go in here and I'm going to create myself a sign chart. So I've got my sign chart, and let's see. I see that x equals 0 is an important number, and x equals 3 halves is an important number. And I want to know what happens here between these. So what I'm going to put up here, this will be the sign of f prime. And I know kind of what's happening. I know at 0 that f prime is equal to 0, and I know at 3 halves f prime is equal to 0. But what about in between these things right here? Are they positive? Are they negative? Or what? Well, it turns out that this is actually pretty straightforward. This is pretty easy to do because all I need to do is go in there and I can identify a number. I need a test number. Okay, so I'm going to find a test number somewhere. Between 0 and 3 halves, I could get the test number of 1. All right, so 1's going to be a test number. And so what I'm going to do is I'm going to plug this number in, plug into f prime to see if it's positive or negative. And that's our strategy here, is we're just going to plug that into f prime and see whether it's f prime is positive or negative. So let's see, if I take a 1 and I put it into f prime, that would give me 4 times 1 cubed minus 6 times 1 squared. Looks like I would get a negative 2 right there. So I know that I've actually got negatives here in this interval. Now I could do the same thing here. I want pluses or minuses, and I could just choose a number over here, like negative 1, negative 2, anything that's over here, plug it in. And the same thing over here. I just need something greater than 3 halves. Pick some test number, plug it in. You get your pluses and minuses. And there's nothing wrong with doing it that way. That's perfectly fine. But if I go back and I remember this cool fact here, the signs only change when the multiplicity is odd. They don't change if the multiplicity is even. So at 0, which has even multiplicity, the signs aren't going to change. So I know I've got negatives over here. And at 3/2, which has odd multiplicity, right? 1 is an odd number, the sign will change. So like I said, if you want to choose test numbers over here and plug them in, fine. You can get your pluses and minuses that way, but it's not exactly the quickest way of doing it. So it looks like from here I can identify a couple of things. One thing is I can identify that I've got a relative max occurring right, a relative min occurring right here, right? Because it's decreasing, hits that 0, increasing, decreasing hits that critical number rather, and then it's increasing. So relative min is happening here, but I don't get anything happening over here, right? That just means the graph is coming down, levels off, comes down again. Okay, so let's go ahead and write down some of the stuff we know. We know that this function is decreasing from negative infinity over until I hit 0. And it's also decreasing from 0 up until I hit 3/2, right? This is your x-axis here, right? So negative infinity, which goes out this way, negative infinity until I hit 0. It's not decreasing at 0, right? Because the slope at the tangent line is 0 there, right? So it's leveling out at that point. But it's decreasing from 0 to 3/2, and so I've got where it's decreasing. This thing is increasing. Let's see, that happens from 3/2 up into infinity, right? This is your x-axis here. It looks like it's increasing from 3/2 all the way out, that way. And so it's increasing there. Other information that I've got is that I know that I've got a relative min. And that relative min is happening at the point 3/2, right? That's where it's decreasing. It's 3/2. It starts increasing. So and remember the 3/2 is the x value there. And 3/2 and whatever the y value is at 3/2. Okay, so 3/2 and f of 3/2. And now to get this number, you would just take 3/2 and go all the way back to your original function up here and plug 3/2 into here. Now it turns out I've already done that, so I'm just going to go ahead and write it down. The relative minimum here is occurring at the point 3/2, and the y value there is negative 27 over 16. And you found the relative min. Okay, so I've got a few more examples, but I think I'm going to do those in another video, and so just consider this to be part 1, and look for video part 2 of the same subject.